Comparative Seismic Analysis of Bare Frame and Frame with Infill Model of Existing State Library Building. A. Prabhakaran 1, Mohd. Saqlain 1, S. Anand Kumar 1, KPUJA 1, Sophia Immanuel 2. UG Student 1, Assistant Professor, G. 2, Department of Civil Engineering. Dr. B. R. Ambedkar Institute of Technology, Port Blair, Andaman and Nicobar Islands. Abstract: the response of an existing structure when subjected to seismic excitation can be evaluated its performance and safety. There are different elastic and inelastic approaches to analyze a structure using equivalent static analysis, linear dynamic analysis, nonlinear static analysis, nonlinear dynamic analysis. In equivalent static analysis method or linear static analysis, the stiffness of the structure remains constant, whereas in nonlinear analysis, the stiffness of the structure varies and the total force is plotted against a reference displacement to obtain a capacity curve. In nonlinear dynamic analyses, the detailed structural model subjected to a ground motion provides estimates of T deformations at each degree of freedom in the model. A numerical simulation is carried out to evaluate the seismic performance of a 3-story already existing state library in Andaman and Nicobar Island. As Andaman and Nicobar Island is located in soft to medium soils, response of the building is analyzed under a simulated earthquake ground motion at Andaman and Nicobar Island site is compared with that under a measured earthquake ground motion of EI-Centro. In this paper, a comparative study of seismic response of a library building modeled as both bare frame and frame with infill is analyzed by the linear analysis, pushover, and time history analysis has been performed using SAP 2000 V18 software as per the IS 1893-2016 Part 1. Keywords: equivalent static analysis, linear static analysis, pushover analysis, nonlinear dynamic, time history analysis, base shear, capacity curve. 1. Introduction. All over the world, there is a high demand for construction of tall buildings due to increasing population and urbanization. Earthquakes have the potential for causing the greatest damages to tall structures. Reinforced concrete multi-storied buildings are very complex to model as structural systems for analysis. Usually, they are modeled as two-dimensional or three-dimensional frame systems using finite beam elements. Since earthquake forces are random in nature and which cannot be predicted, the engineering tools need to be sharpened for analyzing structures under the action of these forces. Krishnaji Nair and Akshara SP 2017. According to the seismic zoning map of IS. 1893 to 2002, India is divided into 4 zones on the basis of seismic activities. They are Zone 2, Zone 3, Zone 4, and Zone V. Andaman and Nicobar Island lies in Zone V. Most of existing buildings do not meet the current design standards due to design shortage or construction shortcomings. There are various reasons such as the lack of a national code, the non-compliance with applicable code requirements, the updating of codes, the design practices and changes in the use of buildings. Therefore, existing buildings should be evaluated regarding their capacity for resisting expected seismic effects before rehabilitation works. Riza Ainul Hakim, Mohammed Sahib Alama and Samir Ashhour 2014. In conventional elastic design analysis method, many important aspects that affect the seismic performance of the building cannot be determined. When a building undergo inelastic deformations under seismic ground motions determines the structural behavior of building. Due to this reason, the evaluation of the building is carried on the basis of inelastic deformation applied demanded by an earthquake, besides the stresses induced by the equivalent static forces as specified in seismic regulations and codes. Nowadays, to estimate seismic demands for a building, pushover analysis is performed. It is a commonly used technique, which provides acceptable results. Pushover analysis is a series of incremental static analysis carried out to develop a capacity curve for the building. This procedure needs the execution of a nonlinear static analysis of the structure that allows the monitoring of the progressive yielding of the structure component. The building is subjected to a lateral load. The load magnitude increases until the building reaches the targeted displacement. This target displacement is determined to represent the top displacement when the building is subjected to design-level ground excitation. Reza Ainul Hakim, Mohammed Sahib Alama and Samir Ashour 2014. Pushover analysis produces a pushover curve or capacity curve that presents the relationship between the base shear, V, and roof displacement, dot. The pushover curve depends on the strength and deformation capacities of the structure and describes how the structure behaves beyond the elastic limit. Nonlinear dynamic analysis is a principally convenient approach. In this, structure is subjected to real-time ground motion of an earthquake which determine the seismic response of a structure. The time history method can be applied to both elastic and inelastic analysis. In elastic analysis, the stiffness characteristics of the structure are assumed to be constant for the whole duration of the earthquake. In the inelastic analysis, the stiffness is assumed to be constant through the incremental time only. 2. Description of structure. In this report, a RC-framed building was taken for analysis, G+2. The RC frame model is subjected to earthquake located in seismic zone V. In the above model, the support condition was assumed to be fixed and soil condition was assumed as medium soil. Fig 2.4 Roof level. 2.2 Modeling and analysis of building. A ground with 3-storied, G+3, existing reinforced concrete building located in Zone V of India was taken for the investigation. This existing building is designed and constructed using IS 456-1978 only for the gravity loads, i.e., without considering the previous seismic code IS 1893-1984. First, the equivalent static analysis of building was done under gravity loads and seismic loads. Then compare the critical forces and moments of beams and columns at face of joint. The modeling and analysis was carrying out first in SAP 2000. Modeling consisted of following steps. 2.2.1 Structural discretization. The beams and columns layout were available. Then the structure was discretized. Discretization includes fixing of joint coordinates and member incidences. 2.2.2 Property specification and support condition. Properties were assigned to the members. The member properties were given. Then support conditions were given to the structure. The support condition given was fixed. 2.2.3 Loading. The self-weight of the members will be taken automatically by the software. Live loads of slabs were entered as floor loads. Live loads were considered as per IS 875, Part 2, 1987. The wall loads were provided to the beam based on provisions in IS 875, Part 1, 1987. Seismic loads were applied automatically by the software and is based on IS 1893, Part I, 2002. A. Live load as per IS 875, Part 2, 1987-11. 3.2 Nonlinear Static Analysis. Nonlinear static analysis, also known as pushover analysis procedure, is mainly used to estimate the strength and drift capacity of existing structure and the seismic demand for this structure subjected to selected earthquake. Pushover analysis, which is an iterative procedure, is looked upon as an alternative for the conventional analysis procedures. Pushover analysis of buildings subjected to increasing lateral forces is carried out until the preset performance level, target displacement, is reached. The promise of performance-based seismic engineering, PBSE, is to produce structures with predictable seismic performance. The recent advent of performance-based design has brought the nonlinear static pushover analysis procedure to the forefront. Pushover analysis is a static nonlinear procedure in which the magnitude of the structural loading along the lateral direction of the structure is incrementally increased in accordance with a certain predefined pattern. It is generally assumed that the behavior of the structure is controlled by its fundamental mode, and the predefined pattern is expressed either in terms of story shear or in terms of fundamental mode shape. With the increase in magnitude of lateral loading, the progressive nonlinear behavior of various structural elements is captured, and weak links and failure modes of the structure are identified. In addition, pushover analysis is also used to ascertain the capability of a structure to withstand a certain level of input motion defined in terms of a response spectrum. Pushover analysis is of two types. I. Force controlled. 5. Conclusion. The base shear obtained from the pushover analysis is maximum among equivalent static and time history analysis. By comparing the base shear obtained from 3 analyses for both bare frame model and frame with infill model, it is concluded that frame with infill model possess high base shear than the bare frame model. In linear analysis, the structure will undergo elastic deformation where all the fibers does not undergo complete deformation, whereas in pushover analysis collapse mechanism makes all the fiber to yield, causing plastic hinges to be formed with unlimited deformation due to rotation of the member. The hinge formation in the bare frame model is more as compared to the frame with infill. In time history analysis, the structure is analyzed for real-time peak ground acceleration, EI-Centro. The structure was safe under the seismic motion as it is designed for its ductile behavior considering zone V as per IS 1893:2002. 5. Acknowledgement. We gratefully acknowledge Dr. Jensen Daniel Hod, Civil Engineering, Dr. B.R. Ambedkar Institute of Technology, Port Blair, Andaman and Nicobar Island for giving us opportunity to perform a real-time project. We would also like to express our thanks to Dr. Utapal Sharma, Principal, Dr. B.R. Ambedkar Institute of Technology, Port Blair, Andaman and Nicobar Island for all necessary support in the entire project.